Hello friends, now we'll start the new chapter, probability. Basic terminologies in this chapter. Concept of probability, addition theorem, conditional probability. These are the topics that we are learning in this chapter. Multiplication theorem, Bayes theorem, odds. Now we'll start the basic terminologies. The random experiment means suppose an experiment having more than one outcome. All possible results are known, but the actual result cannot be predicted. Such an experiment is called a random experiment. This is very simple. Suppose that experiment having more than one outcome, and when we toss the coin, then we have the two outcomes, head and tail. But we cannot say that which will come. All possible results are known, but actual result cannot be predicted. Such an experiment is called the random experiment. Now next, outcome. A possible result of a random experiment is called possible outcome of the experiment. Sample. Now the sample space. The set of all possible outcomes of a random experiment is called the sample space. The sample space is denoted by capital S or the Greek letter omega. The number of elements of S is denoted by n of S. A possible outcome is also called a sample point, since it is an element in the sample space. Now the event. A subset of sample space is called an event. Favorable outcome. An outcome that belongs to specified event is called a favorable outcome. Now the types of event. Elementary event. An event consisting of a single outcome is called elementary event. Single element. Certain event. The sample space is called the certain event if all events, all elements, all possible outcome are favorable outcomes, that is, event consists of the whole sample space. Event consists of the whole sample space. That is the certain event. Next is impossible event. The empty set is called impossible event as no possible outcome is favorable. This is the impossible. Now the algebra of events. Events are subset of the sample space. Algebra of events uses operations in set theory to define new event in terms of known event. Union of two events A and B be two events in the sample space capital S. The union of A and B is denoted by A union B and is a set of all possible outcomes that belongs to at least one of A and B. These are the definition. Exhaustive event, two events A and B in the sample space capital S are said to be exhaustive if A union B is equals to capital S. Now the next is intersection of two events A and B be the two events in the sample space capital S. The intersection of A and B is the event consisting of outcomes that belongs to both the event A and B. A is equals to 1, 2, 3, 4 and B is equals to 2, 4, 5. Then A intersection B is equals to 2, 4. Mutually exclusive events. Event A and B in the sample space capital S are said to be mutually exclusive if they have no outcomes in common. In other words, The intersection of mutually exclusive events is empty. Mutually exclusive events are also called disjoint events. If two events A and B are mutually exclusive and exhaustive, then they are called complementary events. A and B are complementary event, then A union B is equals to S and their intersection is phi. This we have learned in the 9th standard also. Concept of probability. A random experiment has uncertainty regarding the actual result of the experiment, even though all possible outcomes are already known. The classical definition of probability is based on the assumptions that all possible outcomes of an experiment are equally like outcomes, equally likely outcomes, all possible outcomes of, the definition of this is, all possible outcomes of a random experiment are said to be equally likely if none of them can be preferred over the others. Now the probability of an event. This is a simple definition. Probability of an event A is defined as P of A is equals to N of A upon N of S, where N of A is equals to number of outcomes theorable for event A. N of S is equals to number of all possible outcomes element properties of probability, that is the basic properties. A complement, that is A dash is the complement of A, and therefore P of A dash is equals to 1 minus P of A. For any event A in S, the probability lies between 0 and 1 or equal to 0 or equal to 1 also. For impossible event, that is phi, P of phi is 0. For certain event, capital S, P of S is equals to 1. because all the elements are present there, but therefore n of a is equals to n of s, and that's why its a probability is 1. And in this case, the event do not have any single element, and that's why it's a 0 upon n of s, that is equals to 0. If a1 and a2 are mutually exclusive events, then p of a union a1 union a2 is equals to p of a1 plus p of a2. If a is a subset of p, then p of a, probability of a is also less than or equal to probability of b. Probability of a complement intersection b is equals to p of b minus p of a. Addition theorem. For any two events a and b of a sample space capital S, p of a union b is equals to p of a plus p of b minus p of a intersection b. For any two events a and b, p of a intersection b complement is equals to p of a minus p of a intersection b. For any three events a, b, and c of the sample space capital S, p of a union b union c is equals to p of a plus p of b plus p of c minus p of a intersection b minus p of a intersection c, and the last. Now we'll start the exercise 9.1. This is very simple exercise. There are the 4 pens, red, green, blue, and purple, in a text drawer, for which 2 pens are selected at random, one after the other, with replacement. State the sample space and the following. If the 2 pens are selected at random, one after the other, with replacement, the sample space S is given by RR, RG, RB, RP, GG, GR, GB, GP. Next is BB, BR, BG, and in this way. Now see this here problem. There are the 4 pens, red, green, blue, and purple, in a desk drawer, of which 2 pens are selected at random, one after the other, with replacement. State the sample space and the following events. If the 2 pens are selected at random, one after the other, with replacement, the sample space capital S is given by, if is selected first, that is R, then second will be again R, then RG, RB, and RP. If we selected first G, the second will also G, then GR, GB, GP, then B, second will also B, therefore it is a BB, then BR, BG, BP. If we selected, that is a purple, that is PP, PR, PG, and PP. In this way, this is the sample space Now the next is the event A, selecting at least one red pen, then we will have the required, that is a RR, RG, RB, RP, GR, BR and PR. What type of the next event is? The event that two pens of the same color are not selected, that is not required RR, RG, RB, RP, and these are the different. Same color is not repeated. Now see this also. Selecting at least one red pen. Therefore, RR, RG, RB, RP, GR, BR and PR. B is equals to event that two pens of the same color are not selected, and therefore it is a RG, RB, RP, GR, GB, GP, BR, BG, BP, R, PR, PG, PP. It is this we can select from all these here. Now we'll start the next problem. Now we'll start the next problem. A coin and a die are tossed simultaneously. Enumerate the sample space and the following events. The first is A, getting tail and an odd number. B, getting a prime number. C, getting a head and perfect square. When a coin and die are tossed simultaneously, the sample space capital S is given by S is equals to H1, H2 up to the H6, and similarly T1, T2, T3 up to the T6. Now the first is capital A, the event of getting a tail and an odd number, tail and odd number. Now select this is 1, 2, 3. These are the tail and the odd number. B, the event of, I can also write this here. Next is B, the event of getting a head and the prime number, that is H2, H3, H5, T2, T3, T5. C, the event of getting a head. Now this is the second problem. A coin and a die are tossed simultaneously. Enumerate the sample space and the following events. A, getting a tail and an odd number. B, getting a prime number. C. Getting a head and a perfect square when a coin and die are tossed simultaneously. The sample space S is given by. This is very simple sample space. That is S is equals to in curly bracket H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6. Now next A is the event of getting a tail and an odd number. That is A is equals to in curly bracket T1, T3, T5. Next is a B is equals to event of the getting a prime number, that is head or tail prime number, that is a B is equals to in curly bracket H2, H3, H5, T2, T3, T5, and the last C, the event of getting a head and a perfect square, that is H1 and H4. Now we'll see the next problem. Now the problem number 3. Find n of s for each of the following random experiment. That is the first. From an urn containing 5 gold and 3 silver coins, 3 coins are drawn at random. 3 coins can be drawn from an urn containing 8 coins in 8C3 ways. N of s is equals to 8C3, that is 8 factorial upon 8 minus 3 factorial into 3 factorial, 8 factorial upon 5 factorial into 3 factorial, that is equals to 56 if we solve that. Next is B. 5 letters are to be placed into 5 envelopes such that no envelope is empty. Now the first letter can be placed into any of 5 envelopes in 5 different ways. Since no envelope should be empty, therefore second letter can be placed into any of 4 remaining envelopes in 4 different ways. Third letter in 3 different ways. Second letter in 2 different ways, and first, that is the last letter, in 1. Therefore n of s is equals to 5 into 4 into 3 into 2 into 1, that is equals to 120. Therefore n of s is equals to 120. C. 6 books of different subjects are arranged on shelf. That is the 6 books. That is the first book in 6 ways. Second will be in 5 ways, we can arrange it. Third, 4. Fourth is 3 ways. Fifth is 2 ways. And sixth, that can arrange in the single way. Therefore, n of s is equals to 6 into 5 into 4 into 3 into 2 into 1, that is 720. Now the next. 3 tickets are drawn from a box containing 20 lottery tickets. That is, the 3 can be drawn from a box containing 20 lottery tickets in 20 C3 ways. That is, a 20 C3 is equals to 20 factorial upon 20 minus 3 factorial into 3 factorial. We can solve it like this. 20 factorial upon 20 minus 3 factorial into 3 factorial. 20 factorial upon 17 factorial into 3 factorial. Now it can be written as 20 into 19 into 18 into 17. 17 factorial into 3 into 2 into 1. These get cancelled. And therefore, that is 1140. You can also see from here also. Find the n of s. That is, we want to find out the sample space for each of the following random experiment. From an urn containing the 5 gold, 3 silver coins. 3 coins are drawn at random. The first 3 coins are drawn from an urn containing the 8 coins. That is, 8 C3 ways. Therefore, n of s is equals to 8 C3. We can calculate it. And therefore, n of s is equals to 56. Now, next is 5 letters to be placed in the 5 envelope such that no envelope is empty. First letter can be placed into any of the 5 envelopes in 5 different ways. Since no envelope should be empty, second letter can be placed into any of the four remaining envelopes in the 4 different ways, third letter in 3 different ways, second letter in 2 different ways, and the one letter in 1. N of s is equals to 5 into 4 into 3 into 2 into 1, that is equals to 120. N of s is equals to 120. 6 books of the different subjects arranged on a shelf, 6 books. First book in 6 ways, second 5, third 4, fourth 3, fifth book 2 ways, and the sixth is 1. And therefore, if we take the multiplication, that is 6 into 5 into 4 into 3 into 2 into 1, that is equals to 720. Next is 3 tickets are drawn from a box containing the 20 lottery tickets. Therefore, the 3 tickets can be drawn from a box containing 20 lottery tickets in 20 C3 ways. That is, n of s is equals to 20 C3, and that is equals to 20 factorial upon 20 minus 3 factorial into 3 factorial. 20 factorial upon 17 factorial into 3 factorial. If we calculate them, then you will get 1140. Now we'll start the fourth problem. 2 fair dice are thrown. State the sample space and write the favorable outcomes for the following events. A. Sum of the numbers on 2 dice is divisible by 3 or 4. First of all, we will write the sample space. When 2 fair dice are tossed, the sample space, capital S, is given by S is equals to 1 1 1 2 1 3 1 4 1 5 1 6, 2 1 2 2 2 3 2 4 2 5 2 6, 3 1 3 2, 3 3 3 4 3 5 3 6, 4 1 4 2 4 3 4 5 4 6, 4 4 also, 5 1 5 2 5 3 5 4 5 5 5 6, 6 1 6 2 6 3 6 4 6 5 6 6. Therefore, n of s is equals to 36. Now, we require the event. A is equals to event. The sum of the numbers on the two dice is divisible by 3 or 4. Therefore, we select that is a 1, 2, 1, 3, 1, 5, 1, 2, 2, 1, 2, 2, 2, 4, 2, 6, 3, 1, 3, 3, 3, 5, 3, 6, 4, 2, 4, 4, 4, 5, 5, 1, 5, 3, 5, 4, 5, 6, 2, 6, 3, 6, 6. B. Sum of the numbers on two dice is 7. B is equals to in curly bracket that is 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. You can write also this. C is equals to odd numbers on the first die. That is C is equals to event of the odd number on the first die. That is equals to, that is the odd number on the first die. That is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 3, 1, 3, 3, 3, 5, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. D is equals to the event of the even number on the first die. That is a 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. E. Check whether the event A and B are mutually exclusive events, exclusive and the exhaustive. A intersection B is equals to 5 and but A union B is not equals to S. Therefore, A and B are mutually exclusive but not exhaustive. F. Check whether the events C and D are mutually exclusive and exhaustive. C intersection D is equals to C intersection D is equals to 5 and C union D is equals to S. C and D are mutually exclusive and exhaustive. Now we'll see. Now see this here problem. Two fair dice are thrown. State the sample space and write the favorable outcome of the following events. A. The sum of the numbers on the two dice is divisible by 3 or the 4. Now see this. When two fair dice are tossed, the sample space capital S is given by, that is S is equals to 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Now the first event, A is equals to the event that the sum of the numbers on the two dice is divisible by 3 or 4. Therefore, A is equals to in curly bracket 1, 2, 1, 3, 1, 5. This is the first, divisible by 3 or 4. From the second, it's a 2, 1, 2, 4. That is a 2, 2 also, 2, 4, 2, 6. 3, 1, 3, 3, 3, 5. From the third row, 3, 6, 4, 2, 4, 4, 4, 5. 5, 1, 5, 2, 5, 3, 5, 4. 6, 2, 6, 3, 6, 6. Now, next is B. The sum of the numbers on the two dice is 7. That is B is equals to in curly bracket 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. And C, the odd number on the first die. C is equals to event of the odd number on the first die. That is a 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. 3, 1, 3, 3, 3, 5. 5, 1, 5, 2, 5, 3. 5, 4, 5, 5, 5, 6. D, the event of the even number on the first die. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Check whether A and B are mutually exclusive and exhaustive. If we take the A intersection B, that is equals to 5. But A union B is not equals to S. Therefore, A and B are mutually exclusive but not exhaustive. Now, the next is check whether the events C and D are mutually exclusive and exhaustive. C intersection D is equals to 5 and C union D is equals to S. Therefore, C and D are mutually exclusive and exhaustive. See the next. Question number 5. A bag contains 4 cards marked 5, 6, 7 and 8. Find the sample space if 2 cards are drawn at random A with replacement, B without replacement, two cards are drawn from the cards marked as the 5, 6, 7, 8. If the 2 cards are drawn with replacement, the sample space capital S is given by S is equals to 5, 5, 5, 6, 5, 7, 5, 8, 6, 5, 6, 6, 6, 7, 6, 8, 7, 5, 7, 6, 7, 7, 7, 8, 8, 5, 8, 6, 8, 7, 8, 8. B, if the 2 cards are drawn without replacement, the sample space S is given by that is 5, 6, 5, 7, 5, 8, 6, 5, 6, 7, 6, 8, 7, 5, 7, 6, 7, 8, 8, 5, 8, 6, 8, 7. Now we'll see. You can summarize this problem also. A bag contains the 4 cards marked 5, 6, 7, 8. Find the sample space if the 2 cards are drawn at random with replacement and without replacement. That is, the two cards are drawn from the cards marked as the 5, 6, 7, 8. If the cards are drawn with replacement, then you will have this type of the 5, 5, 5, 6, 5, 7, 5, 8, 6, 5, 6, 6, 6, 7, 6, 8, 7, 5, 7, 6, 7, 7, 7, 8, 8, 5, 8, 6, 8, 7, 8, 8. If cards are drawn without replacement, the sample space capital S is given by 5, 6, 5, 7, 5, 8, 6, 5, 6, 7, 6, 8, 7, 5, 7, 6, 7, 8, 8, 5, 8, 6, 8, 7. Now the next is a fair die is thrown. Problem number 6 is thrown 2 times. Find the probability that the sum of the numbers on them is 5. S is equals to 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2. These are the very simple. 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. This is the sample space. Let capital A is equals to event that the sum of the number is 5. And then it is a 1, 4, 2, 3 from the third, 3, 2, 4, 1. Therefore, n of A is equals to 4. P of A is equals to n of A upon n of S. And that is equals to 4 upon 36 is equals to 1 upon 9. Sum of the numbers on them is at least 8. B is equals to event that the sum of the numbers is at least 8. B is 2, 6, 3, 5, 4, 4, 5, 3, 6, 2, 3, 6, 4, 5, 5, 4, 6, 3, 4, 6, 5, 5, 6, 4, 5, 6, 6, 5, 6, 6. NB is equals to N of B is equals to 15. Therefore, P of B is equals to N of B upon N of S. 15 upon 36, and that is nothing but 5 upon 12. Therefore, P of B is equals to 5 upon 12. Next is C. The first row gives multiple of 2 and second row gives a multiple of 3. Let C is equals to the event that 2, 3, 2, 6, 4, 3, 4, 6, 6, 3, 6, 6. Therefore, now multiple of the 2. First row, that is a 2, 2. Next is a multiple of 2 is 4. Multiple of 2, multiple of 2. And multiple of the 6 is also 2. Next, second row means what? This is a 3, 6, 3, 6. Now this is 3, 6. Second row, second row, second row. All these are multiple of the 3. Therefore, N of C is equals to 6. Therefore, P of C is equals to N of C upon N of S. 6 upon 36, that is 1 upon 6. P of C is equals to 1 upon 6. D. Product of numbers on them is 12. That's D is equals to 2, 6, 3, 4, 4, 3, 6, 2. N of D is equals to 4. Therefore, P of D is equals to 4 upon N of D upon N of S. 4 upon 36. That is 1 upon 9. A fair die is thrown 2 times. Find the probability that the sum of the numbers on them is a 5. Now first of all we will write this is a sample space. I had repeated here. Therefore I will not repeat even here. Now what type of the events that we required? कोणत्या प्रकारचे आपल्याला events पाहिजे? A is equals to the event that the sum of the number is 5. Therefore A is equals to 1, 4, 2, 3, 3, 2, 4, 1. Therefore N of A is equals to 4. P of A is equals to N of A upon N of S. That is equals to 4 upon 36, and that is equals to 1 upon 9. And what about the next? B. The sum of the number on them is at least 8. Therefore, you can write it here. That is a 2, 6, 3, 5, 4, 4, 5, 3, 6, 2, 3, 6, 4, 5. At least. कमीत कमी 8 असली पाहिजे. Minimum 8 requirement. 5, 3, 6, 3, 4, 6, 5, 5, 6, 4, 5, 6, 6, 5, 6, 6. Therefore, N of B is equals to 15. P of B is equals to N of B upon N of S. 15 upon 36, 5 upon 12. P of B is equals to 5 upon 12. The first row gives a multiple of 2 and the second row gives a multiple of 3. First row 2, 2, 4, 4, 6, 6. Multiple of the 2 means these are the multiple of the 2. And second row is a multiple of the 3. That is a 3, 6, 3, 6, 3, 6. All are multiple of 3. Therefore, N of C is equals to 6. Therefore, the P of C is equals to N of C upon N of S. 6 upon 36, 1 upon 6. Therefore, P of C is equals to 1 upon 6. Next is the product of the number on them is 12. That is D is 2, 6, 3, 4, 4, 3, 6, 2. Therefore, N of D is equals to 4. Therefore, P of D is equals to N of D upon N of S. And that is a 4 upon 36. That is equals to 1 upon 9. Now, the next problem is problem number 7. 2 cards are drawn from a pack of 52 cards. Find the probability that one is a face card and other is an S card. That is, 2 cards can be drawn in 52 C 2 ways. This is the first. This is a 52 C2. Therefore, we can find out from the combination, that is a n factorial upon n minus r factor into r factorial. Therefore, 52 into 51 into 50 upon 50 factor into 2 factorial. These two get cancelled. That is a 26 into 51. Therefore, n of s is equals to 26 into 51. A is equals to the event that one is a face card and other is an S card. Now we have the total 12 face card. Therefore, the 12 face cards are there. The card drawn is a 12C1, that is equals to 12X. And another is a S, that is a 4C1. That is equals to 4 ways. Therefore, n of a is equals to 4 into, that is a 12 into 4, that is equals to 48. Therefore, P of a is equals to n of a upon n of s, 48 upon 26 into 51, that is equals to that is 8 upon 221. P of A is equals to 8 upon 221. B, 1 is a club and other is a diamond. B is equals to event that 1 is a club and the other is a diamond. One club can be drawn from, that is a 13C1 and that is equals to 13 base. Similarly, 1 is a diamond, that is again 13 diamond cards, similar to the club 13 cards, that is equals to 13C1, that is equals to 13 base. Therefore, the required probability is equals to P of B is equals to N of B upon N of S, that is equals to 13 into 13 upon 26 into 51, that is equals to 13 upon 102. Therefore, the required probability is 13 upon 102. C, both are from the same suit. That's again important. That is, C is equals to event that the both are from the same suit. Therefore, one suit can be selected in 4C1 ways. That is 4C1. To select the first of all, what type of the suit will be here? 4C1 is equals to 4. Two cards are drawn from the selected suit in 13C2. That is 13 factorial upon 13 minus 2 factorial into 2 factorial. That is equals to 13 into 12 into 11 upon 11 into 2. That is equals to 13 into 6 is equals to 78. Both cards can be chosen from the same suit in 4 into 13 into 6. The required probability P of C is equals to N of C upon N of S. That is 4 into 13 into 6 upon 26 into 51. That is equals to 4 upon 17. This is the required probability P of C. P of C is equals to 4 upon 17. Both are red cards. D is equals to event that both cards are the red cards. There are 26 red cards. Two red cards can be chosen from 26C2 ways. Therefore, it is written as in this manner. Therefore, that is the 26C2 is equals to 26 factorial upon 26 minus 2 factorial into 2 factorial, and that is equals to 13 into 25. Therefore, the required probability, that is P of D, is equals to N of D upon N of S, 13 into 25 upon 26 into 51. Therefore, P of D is equals to 25 upon 105. P of D is equals to 25 upon 105. Now, the next is, one is hurt card and the other is non-hurt card. E is equals to the event that one card is hurt and other is a non-hurt card. One hurt can be drawn from the 13 and the remaining is from the 39. Therefore, it is a 13C1. Non-hurt can be drawn in 39C1, that is a 39 base. One hurt and one non-hurt can be drawn in 13 into 39 ways. Therefore, N of E is equals to 13 into 39. The required probability P of E is equals to N of E upon N of S. 13 into 39 upon 26 into 51. And that is equals to 13 upon 34. Therefore, P of E is equals to 13 upon 34. Now we'll see this again. Again, we can summarize this problem. Two cards are drawn from the pack of 52 cards. Find the probability that one is a face card and the other is a ace card. That is, the two cards can be drawn from the 52 cards in 52 C2 ways, and that is equals to 52 factorial upon 20, 52 minus 2 factorial into 2 factorial. This is the way. That is equals to N of S is equals to 26 into 21. So this here. Next is A, the event that one is a face card and the other is an ace card. One face can be drawn from the 12 face card. That is a 12C1. That is equals to 12 ace. And 4C1. That is, there are the 4 ace card. Therefore, it is a 4C1 that is equals to 4 ace. Therefore, now the next is P of A is equals to N of A upon N of S, 8 upon 221. This is the P of A. One is a club and the other is a diamond card. B, the event of club and the other is a diamond. That is 13C1 and 13C1 for the club and for the diamond. Therefore, the required event N of B is equals to 13 into 13. Therefore, P of B is equals to N of B upon N of S, 13 into 13 upon 26 into 51, 13 upon 102. And that's why required probability is equals to 13 upon 102. Both are from the same suit. C is equals to the event that both cards are from the same suit. One suit can be selected from the suit in the 4C1 ways, and the two cards can then be drawn from the selected suit in 13C2. Therefore, 13 factorial upon 13 minus 2 factorial into 2 factorial, then you will get 78. And that's why the required probability, that is the event, is 4 into 13 into 6. Therefore, P of C is equals to N of C upon N of S. Therefore, the required probability P of C is equals to 4 upon 17. Now, both are the red cards. D is the event that both are the 26 red card. 26C2, then we can write this 26 factorial upon 26 minus 2 factorial into 2 factorial. Therefore, P of D is equals to N of D upon N of S. 13 into 25 upon 26 into 51. Therefore, P of D is equals to 25 upon 105. One is a hurt card and the other is a non-hurt card. Let E, the event that one card is hurt and the other is a non-hurt. One hurt can be drawn in 13 hurt, that is the 13C1 is equals to 13 beds. Non-hard card, there is a, how many? That is a 39 non-hard card other than hard. Therefore, 13C1 is equals to 39 beds. Therefore, 13 into 39, therefore required probability, that is equals to P of E is equals to N of E upon N of S. We can calculate it. That is equals to 13 upon 34. Now the problem number 8. 3 cards are drawn from a pack of 52 cards. Find the chance that 2 are queen cards and 1 is ace card. Therefore, the 3 cards can be drawn from 52 cards. Therefore, the sample space is 52 C3 ways. N of S is equals to 52 C3. Let A is equals to the event that the 2 are queen cards and 1 is an ace card. 2 queens, there are the 4 queens, therefore it is a 4-2 C ways, and 1 is ace, there are the 4 ace card, therefore it is a 4C1. Overall, we are drawing 3 cards, 2 plus 1, that is it, this is the 3. Therefore, two queens and 1 ace can be drawn in 4C2 into 4C1 ways. Therefore, N of A is equals to 4C2 into 4C1. The required probability P of A is equals to N of A upon N of S. 4C2 into 4C1, that is 52 C3, and that is equals to 4 factorial upon, we can simplify it like this, 4 factorial upon 4 minus 2 factorial into 2 factorial, 4 factorial upon 4 minus 1 factorial into 1 factorial. Therefore, after the simplification, we will get therefore 6 upon 5,525 P of A is equals to 6 upon B. At least one is diamond card. B, the event that at least one is a diamond card. B dash, the event that all cards are non-diamond cards. Non-diamond. There are 39 non-diamond cards and 3 non-diamond cards can be drawn from these 39 cards in 39 C3 ways. Therefore, the N of B dash is equals to 39 C3. Therefore, N of B dash is equals to P of B dash is equals to N of B dash upon N of S. That is, we will find out this answer from by using the complement probability. Therefore, N of B dash upon N of S is equals to 39 C3 upon 52 C3. And after the simplification, then we'll solve 39 factorial upon 39 minus 3 factorial into 3 factorial. And 52 C3 for this is 52 factorial upon 52 minus 3 factorial into 3 factorial. Therefore, after simplification, you will get 39 into 38 into 37, 36 into 36 factor into 3 factorial, 3 factorial into 49. We can cancel it. 39 into 38 into 37, 52 into 51 into 50, and after calculus 703 upon 1700. Therefore, the required probability P of B is equals to 1 minus, we'll find out by using the complement probability. That is 1 minus 703 upon 1700. That is a 997 upon 1700. That is a calculations. P of B is equals to 997 upon 1700. See, all are from the same suit. C is equals to the event that 3 cards are from the same suit. One suit can be selected from 4 suit in 4C1, that is equals to 4 ways. 3 cards can be then drawn from the selected suit, that is 13C3. Therefore, the required probability is equals to P of C is equals to N of C upon N of S. 4C1 into 13C3 upon 52C3. 4 into 13 factorial, 13 minus 3 factorial into 3 factorial. 52 minus 3, 52 factorial, this is the calculation. That is 52 factorial upon 52 minus 3, bracket complete factorial, 3 factorial. That is 4 into, that is we can perform this calculation. That is 4 into 13 into 12, 11 into 10 factorial, 49 factorial into 3 factorial, 10 factorial, 3 factorial into 52 factorial, cancellations. Therefore, the required probability, this is the cancellations. That's 22 upon 425. Therefore, P of C is equals to 22 upon 425. D. They are a king, queen, and the jack. Therefore, they are king, queen, and the jack. From the same suit, that is a one suit can be selected from the same suit, that is a 4C1, 4C1 and the 4C1. This is the event, and the N of S is equals to 52 C3. Therefore, the P of D is equals to N of D upon N of S. 4C1 into 4C1 into 4C1. N of S is equals to 52 C3. That is a 4 into 4 into 4 upon 52 factorial. This is the calculation. Can perform this. (16 upon 5,525). Therefore, P of D is equals to 16 upon 5,000. Three cards are drawn from a pack of 52 cards. Find the chance that the two are the queen cards and the one is a ace card. Three cards can be drawn from the 52 cards in 52 C3 ways. That is, n of S is equals to 52 C3. A is equals to event that the two are the queen cards and one is ace card. Therefore, two queens means what? 4C2 ways, and one ace means what? 4C1 ways. That is, a two queen and the one ace can be drawn in 4C2 and to 4C1 ways, and therefore n of A is equals to 4C2, 4C1. Therefore, P of A is equals to n of A upon n of S, and that is equals to 4C2 into 4C1. That is 52C3, and after calculation, therefore we will get. That is a 4 factorial upon 4 minus 2 factorial into 2 factorial. Next is a 4C1, that is 4 factorial upon 4 minus 1 factorial into 1 factorial. This is the calculation. That is a 6 upon 5,525 P of A. Now, next is at least one is a diamond card. Now, we will find out this by using the complement of the probability. That is, at least one means what? There are the non-diamond cards, and then by using the complement definition of the complement probability, that is, the B is equals to the event that at least one is a diamond card, B dash. The event that all are the non-diamond cards. There are the 13 non-diamond cards, and 3 non-diamond cards can be drawn from the 39C3 ways. Therefore, n of B dash is equals to 39C3, and P of B dash is equals to n of B dash upon n of S, 39C3 upon 52C3. After the calculation, we can get like this. This is the number of the types calculations. पुन्हा पुन्हा या type ची calculations येत आहेत. That is 703 upon 1700. Therefore, the required probability of B is equals to 997 upon 1700. All are from the same suit. C is equals to the event that 3 cards are from the same suit. One suit can be selected in 4C1 ways, that is equals to 4. 3 cards can be drawn from the selected suit in 13C3. Therefore, the required probability P of C is equals to n of C upon n of S, and therefore 4C1 into 13C3 upon 52C3, and the required 4 into 13 factorial upon 13 minus 3 factorial into 3 factorial, 52 factorial upon 52 minus 3 factorial into 3 factorial. These are the calculations, we can perform it, and that is equals to 22 upon 425. Therefore, P of C is equals to 22 upon 425. Now the D, the event that a king, queen and the jack. Therefore, there are the 4 cards n of d is equals to 4c1, 4c into 4c1 into 4c1. N of s is equals to 52c3. Therefore, P of d is equals to n of d upon n of s. 4c1 into 4c1 into 4c1, 52c3. Therefore, 4 into 4 into 4 upon 52 factorial, 52 minus 3 factorial into 3 factorial. And after calculations, you will get that is a 16 upon 5,525. That is a 6. This is it. Now the problem number 9. From a bag containing 10 red, 4 blue and 6 black balls, a ball is drawn at random. Find the probability of drawing a red ball. Now the total number of the balls is 10 plus 4 plus 6, that is equals to 20. One ball is can be drawn from the 20 balls in 20C1, that is equals to 20 factorial upon 20 minus 1 factorial into 1 factorial. 20 into 19 factorial, that is equals to 20 ways. Therefore, n of s is again, that is n of s is equals to 20. A is equals to event that the ball drawn is a red ball. One is red ball. A red ball can be drawn from 10 red balls in 10C1 ways, 10 factorial upon 10 minus 1 factorial into 1 factorial. 10 into 9 factorial upon 9 factorial, that is a 10 ways. N of A is equals to 10. Therefore, the required probability P of A is equals to N of A upon N of S, that is equals to 10 upon 20, that is equals to 1 upon 2. B, a blue or a black ball. Now, whenever there is a or, we add them. That is a B is equals to the event that the ball drawn is blue or black ball. There are 10 blue or the black balls. One ball can be drawn from them in 10C1, that is a 10 beds. N of B is equals to 10. The required probability N of B upon N of S is equals to 10 upon 20, that is equals to 1 upon 2. P of B is equals to 1 upon 2. C, not a black ball. The C is equals to event that the ball drawn is a non-black ball. There are 14 non-black balls. One ball can be drawn from these in 14C1 ways. Therefore, N of C is equals to 14. Therefore, the required probability is equals to N of C upon N of S. 14 upon 20, that is equals to 7 upon 10. Therefore, the required probability 7 upon 10. Now, see this here. A bag containing the 10 red, 4 blue and the 6 black balls. A ball drawn at a random. Find the probability of the drawing a red ball. The red are the 10. Total number of the balls is 20. 4 plus 10 plus 4 plus 6. One ball is drawn at random. Therefore, the sample space is a 20C1. 20 factorial upon 20 minus 1 factorial into 1 factorial. That is equals to 20, where n of s is equals to 20. A, the event that the ball drawn is a red ball. One red ball can be drawn from the 10 red ball in 10C1. That is the 10 factorial upon 10 minus 1 factorial into 1 factorial. 10 into 9 factorial upon 9 factorial into 1. That is the 10 ways. N of A is equals to 10. The required probability P of A is equals to N of A upon N of S. 10 upon 20. That is equals to 1 upon 2. P of A is equals to 1 upon 2. Next is blue or black. That is the event that the ball drawn is the blue or the black. That is, we have seen that there are the 4 blue and the 6 black. Therefore, the total are 6 plus 4. That is equals to 10. One ball can be drawn from the 10C1 base. That is, N of B is equals to 10. Therefore, the required probability P of B is equals to N of B upon N of S, 10 upon 20, and that is equals to 1 upon 2. Therefore, P of B is equals to 1 upon 2. Not a black ball. That is, other than the black balls, there are the 6 black balls. Therefore, the total are 20. Therefore, there are 14 non-black balls. Therefore, the 14C1, you can see this here. So, 14C1, therefore, that is 14 ways. Therefore, N of C is equals to 14. The required probability P of C is equals to N of C upon N of S, and that is equals to 14 upon 10. That is 7 upon 10. Therefore, the required probability is 7 upon 10. Now, the 10th problem. A box contains 75 tickets numbered 1 to 75. A ticket is drawn at random from the box. Find the probability that number on the ticket is divisible by 6. One ticket is drawn at random from the tickets numbered 1 to 75. Therefore, sample space is given by N of S, that is 1, 2, that is 3, 4 up to the 75. N of S is equals to 75. A is equals to the event that the number on the ticket is divisible by 6. That is 6, 12, 18, 24. And the last is 72. Therefore, N of A is equals to 12. That is the total number which are divisible by 6 is 12. N of A is 12. Therefore, P of A is equals to N of A upon N of S. That is 12 upon 75. That is 4 upon 25. Therefore, P of A is equals to 4 upon 25. B. The number on the tickets is perfect square. Therefore, B is equals to the number on the ticket is a perfect square. B is equals to the perfect square are 1, 4, 9, 16, 25, 36, 49, 64. N of B is 8. P of B is equals to N of B upon N of S, 8 upon 75. Therefore, P of B is equals to 8 upon 75. And the next is a number on the ticket is a prime number. C is equals to event. The number on the ticket is a prime number. Therefore, C is equals to 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73. Therefore, N of C is a 21. Therefore, P of C is equals to N of C upon N of S, that is a 21 upon 75, and that is equals to 7 upon 25. D. The number on the ticket is divisible by 3 and 5. Therefore, D is equals to event that the number on the ticket is divisible by 3 and 5. That is by 15. 3 and 5 means it must be the both. We require 3 and 5. It means that is a divisible by 15. That is a 15, 30, 45, 60, 75. N of D is equals to 5. Therefore, P of D is equals to N of D upon N of S. 5 upon 75, that is equals to, now we see again this. The same thing is repeated again. I am repeating this problem. A box contains the 75 tickets numbered from 1 to 75. A ticket is drawn at random from the box. Find the probability that the number on the ticket is divisible by 6. One ticket is drawn from the ticket numbered from 1 to 75. Therefore, the sample space S is given by S is equals to 1, 2, 3, 4 up to the 75, and of S is 75. A is equals to the event that the number on the ticket is divisible by 6, and therefore the numbers are 6, 12, 18, 24 up to the 72. N of A is 12, therefore P of A is equals to N of A upon N of S, 12 upon 75, and that is equals to 4 upon 25, therefore P of A is 4 upon 25. The next is the number on the ticket is a perfect square. B is equals to number on the ticket is a perfect square. B is equals to 1, 4, 9, 16, 25, 36, 49, 64. N of B is 8. P of B is equals to N of B upon N of S, 8 upon 75. Therefore, P of B is equals to 8 upon 75. C, the number on the ticket is a prime. That is a C is equals to the event that the number on the ticket is a prime number, and the numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73. Therefore, P of C is equals to N of C upon N of S, 21 upon 75, and that's its probability is P of C is equals to 7 upon 25. The number on the ticket is divisible by 3 and 5. It means that it must be divisible by 15. And these are the numbers. That is 15, 30, 45, 60, 75. N of D is equals to 5. Therefore, P of D is equals to N of D upon N of S. And that's why the required probability is 1 upon 15. Now the problem number 11. What is the chance that a leaf year selected at random will contain 53 Sundays? A leaf year, now this year is also a leaf year, that is a 2020, 2020. A leaf year has a 366 days, that is a 366 is equals to 52 into 7 plus 2. We can split up. This is the number of the weeks plus 2 days. We have the extra. That is there are the 52 weeks and the 2 other days. These 2 days can be Sunday, Monday, Monday, Tuesday, Tuesday, Wednesday, Wednesday, Thursday, Thursday, Friday, Friday, Saturday, and Saturday, Sunday. If you see this year, that is we have the 2 times Sunday here, that is a Sunday, Monday, and the last is Saturday, Sunday. Therefore, there are the 7 possibilities if you count all the possibilities. That is 1, 2, 3, 4, 5, 6, 7. 7 possibilities. Out of the 7 possibilities, in 2 possibilities we have the Sunday. Therefore, there are the 7 possibilities and the favorable cases are there too. Therefore, the required probability is 2 upon 7. Now, a leaf year is, what is the chance that a leaf year selected at random will contain 53 Sundays? A leaf year has 366 days. That is, 366 is equals to 52 into 7 plus 2. There are 52 weeks and the 2 other days. Therefore, the 2 days can be Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. There are the 7 possibilities and favorable cases are the 2 because there is a Sunday, Monday and the Saturday, Sunday. These are the favorable cases. Therefore, the required probability is 2 upon 7. Now the problem number 12. Find the probability of getting both red balls when from a bag containing 5 red, 4 black balls, 2 balls are drawn with replacement and without replacement. The replacement means what? We again keep there, whatever that we have selected. There are now 9 balls, 5 red, 4 black. Total is 9. When balls are drawn with replacement, n of s is equals to 9 into 9. Therefore, n of s is equals to 9 into 9. Therefore, 9 into 9, that is equals to 81. Both are red can be drawn in 5 into 5, that is equals to 25 ways. Therefore, the required probability, that is 25 upon 81. Second, when balls are drawn without replacement, first ball can be drawn in 9 ways. After that, second ball can be drawn in 8 ways. Therefore, n of s is equals to 9 into 8, that is equals to 72. First is red ball can be drawn in 5 ways and ball is not replaced. Therefore, the second red ball can be drawn from 4 ways. Therefore, the 2 red balls can be drawn in 5 into 4, that is equals to 20 ways. Therefore, the required probability is equals to 20 upon 72, that is equals to 5 upon 18. Now, find the probability of getting the both red balls when from a bag containing 5 red and the 4 black balls, 2 balls are drawn with replacement, without replacement. Now 5 plus 4, therefore total are the 9 balls. When balls are drawn with replacement, n of s is equals to 9 into 9, n of s is equals to 81. Both red balls can be drawn in 5 into 5, that is equals to 25 ways. The required probability 25 upon 81. When balls are drawn without replacement, the first ball can be drawn in 9 ways. After that, the second ball can be drawn in 8 ways. That is, n of s is equals to 9 into 8. That is a 72. First red ball can be drawn in 5 ways. the ball is not replaced, the second ball, red ball, can be drawn in 4 ways, and therefore that is a 2 red balls can be drawn in 5 into 4, that is equals to 20 ways. Therefore the required probability is 20 upon 72, and that is nothing but that is a 5 upon 18. Now the problem number 13. A room has 3 sockets for the lamps from a collection of 10 bulbs, of which 6 are defective. At night, a person selects 3 bulbs at random and put them in a socket. What is the probability that room is still dark? Second, the room is light. Now the 3 balls can be drawn from the 10 bulbs in 10C3 ways, that is the 10 factorial upon 10 minus 3 factorial into 3 factorial, and that is equals to 10 into 9 into 8 into 7 factorial, 7 into 3 into 2 into 1. Therefore 10C3, n of s is equals to 120. Now the first, the room is still dark, that is, let A is equals to event that the room is dark and A complement, that is a room is a light. For A to happen, all 3 bulbs must be drawn, must be chosen from 6 defective bulbs, because there are the 6 defective bulbs. Therefore, these can be done in 6 ways. Therefore, n of A is equals to 6C3, and that is equals to 6 factorial upon 3 factorial into 3 factorial. N of A is equals to 20. Therefore, P of A, that is a room is dark. Therefore, P of A is equals to n of A upon n of S. That is a 20 upon 120. That is a 1 upon 6. P of A is equals to 1 upon 6. Second, the required probability P, the room is light. That is, we find out it's a complement. That is equals to P of A complement is equals to 1 minus 1 upon 6, and that is equals to 5 upon 6. Now again we will see this. A room has 3 sockets for the lamps from a collection of 10 bulbs, of which 6 are defective. At night, a person selects the 3 bulbs at random and put them in a socket. What is the probability that room is still dark, room is light? 3 bulbs can be drawn from the 10 bulbs in n of s is equals to 10C3, 10 factorial upon 10 minus 3 factorial into 3 factorial, and after calculation you will get n of s is equals to 120. First, the room is still dark. Therefore, A, the event that the room is dark, A complement the event that the room is light. For A to happen, all 3 bulbs must be chosen from 6 defective bulbs. This can be done in 6 ways. Therefore, n of A is equals to 6C3, 6 factorial upon 3 factorial into 3 factorial, And after the calculation, you will get n of a is equals to 20. The room is dark, therefore P of a is equals to n of a upon n of s, 20 upon 120, and therefore the P of a is equals to 1 upon 6. And now next is a required property. P is equals to, the room is light, P of a complement is equals to 1 minus 1 upon 6, and that is equals to 5 upon 6. Therefore, P of a complement is equals to 5 upon 6. Now the problem number 14. Letters of the word mother are arranged at random. Find the probability that in the arrangement vowels are always together. There are the 6 letters mother, M-O-T-H-E-R, in the word mother, which O and E are the vowels, can be arranged among themselves. That is 6p6. This is the arrangement. Whenever there is arrangement, we take the permutations that we learn in the permutations and the combination. Therefore, that is a 6p6, that is equals to 6 factorial. And therefore, n of s is equals to 6 factorial bx. Now, let A, the event that vowels are together, the word has 2 vowels, that is O and E, and 4 consonant, that is M, E, H, R. The 2 vowels can be arranged together in 2p2 ways, that is a 2 factorial, 2 ways. Now, considering these vowels as a one group, we can arrange 4 consonants and one group of the vowels, that is 1 plus 4, that is equals to 5, 5p5, that is equals to 5 factorial. This is the arrangement, that's why we are taking the permutation, that is equals to 120. Therefore, n of a is equals to 2 into 120, and P of a is equals to n of a upon n of s, that is a 2 into 120 upon 720, and that is equals to 1 upon 3. B, vowels are never together. Let B, the event that the vowels are not together. That is, we find out the complement of the above probability. B is equals to A bar, that is the complement of that. In first case, we say that the vowels are together. Now, in this case, we say that the vowels are not together. Therefore, the P of B is equals to P of A complement, that is the 1 minus P of A, that is equals to 1 minus 1 upon 3, and that is equals to 2 upon 3. Next, C. O is at the beginning and end with T. The event that O is at the beginning and end with the T. Now these two are the fixed. Therefore, the position of the first and last is fixed. The remaining 4 letters can be arranged in the 4p4 ways. That is a 4 factorial. That is equals to 24 ways. Therefore, n of c is equals to 24, and therefore p of c is equals to n of c upon n of s, that is a 24 upon 720, and that is equals to 1 upon 30. Now next is D. Let D be the event that the arrangement starts with oval and ends with consonant. Now in this case, that is, we have the two ovals. They can be arranged in two ways. First place can be chosen in the 4C1. Ovals can be chosen in the 4C1 ways. The four letters can be arranged in 4P4 ways. The remaining four letters can be arranged, that is a 4P4. Therefore, n of D is equals to 2 into 4 into 24. That is the first, that is the oval can be arranged in the two ways because we have the two. And last will be arranged in the 4 times. And the remaining 4 can be arranged in the 24. Therefore, the P of D is equals to n of D upon n of S. That is equals to 4 upon 15. Therefore, P of D is equals to 4 upon 15. Now we'll see here. Now the again explanation. 14 letters of the word mother can be arranged at random. Find the probability that the arrangement ovals are together. There are the 6 letters in the word mother, which can be arranged among themselves in the 6p6 ways, that is a 6 factorial. N of s is equals to 6 factorial. A, the event that the ovals are together. The word has a 2 ovals, that is OE, and the constants are the 4, that is M, T, H, R. The 2 ovals can be arranged in 2p2 ways, that is a 2 factorial, that is equals to 2 ways. Now considering these ovals as a one group, we can arrange a 4 consonant and one group of the ovals, that is 1 plus 4, that is equals to 5. Therefore 5p5, 5 factorial, that is equals to 120. N of A is equals to 2 into 120. Therefore P of A is equals to N of A upon N of S, 2 into 120 upon 720, that is equals to P of A is equals to 1 upon 3. Ovals are never together. Let B be the event that the ovals are not together. Therefore, we can find out by using the complement of the probability. That is, the B is equals to A complement. That is, P of B is equals to P of A complement. That is equals to 1 minus P of A. 1 minus 1 upon 3. And that is equals to P of A is equals to 2 upon 3. O is at the beginning and end with the T. That's the C. The event that O is at the beginning and end with the T. The position of the first and last letter are the fixed. The remaining 4 can be arranged in the 4 factorial, that is a 4p4, that is a 4 factorial. That is equals to 24 ways. Therefore, n of c is equals to 24. P of c is equals to n of c upon n of s, 24 upon 720. That is, P of c is equals to 1 upon 30. And D be the event that the arrangement starts with the ovals and end with the consonant. Therefore, the ovals are of the first place can be chosen in the 4C1 ways, that is a 4, and the remaining are the 4P4 ways. These are the remaining letters, and the ovals can be chosen in the 2 ways. Therefore, the 2 ovals, therefore they can be chosen in the 2 ways, and that's why that is the n of D is equals to 2 ways of the ovals, 4 ways of the consonant, and the remaining 4 can be arranged in the 24 ways. Therefore, the P of D is equals to N of D upon N of S. That is the 2 into 4 into 24 upon 720. That is equals to 4 upon 15. Therefore, P of D is equals to 4 upon 15. Now next, 4 letters are to be posted in 4 post boxes if any number of the letters can be posted in any of the 4 post boxes. What is the probability that each box contains only one letter? Now any number of the letter can be posted in any of the 4 post boxes. Each letter can be posted in 4 ways. Therefore, N of S is equals to 4:4. Let the event that each box contains only one letter, the first can be posted in 4 post boxes in 4 different ways. Since each box contains only one letter, the second letter can be posted in remaining 3 post boxes in 3 ways, 3 different ways. Since that is a similarly, the third letter can be posted in 2 different ways, and the fourth last, that is a fourth letter in the fourth box. Therefore, N of A is equals to 4 into 3 into 2 into 1. That is equals to 24. P of A is equals to N of A upon N of S. That is a 24 upon 4:4. And that is equals to 6 into 4 upon 4 into 4 into 4, 4. And that is equals to 3 upon 32. Therefore, P of A is equals to 3 upon 32. Now, see again here. That is 4 letters can be posted in 4 post boxes if any number of the letters can be posted in any of the 4 post boxes. What is the probability that each box contains only one letter? Now any number of the letters can be posted in any of the 4 post boxes. Each letter can be posted in 4 ways. That is N of S is equals to 4:4. Let A be the event that each box contains only one letter. The first letter can be posted in 4 different ways, second in 3 ways, third in 2 ways, and the last in 1 way. Therefore, N of A is equals to 4 into 3 into 2 into 1. And that is equals to 24. And P of A is equals to N of A upon N of S. That is 24 upon 4:4. That is equals to their multiplication, division, 4 into 4 into 4. That is a 3 upon 32. This is the recall. Now the problem number 16. 15 professors have been invited for a round table conference by Vice Chancellor of University? What is the probability that two particular professors occupy the seats on either side of Vice Chancellor during the conference? That is the 15 professors plus one Vice Chancellor, that is equals to 16%. Its 16% can be arranged in a round table in 16 minus 1 factorial. That this we have learned in the permutations and the permutation chapter topics. That 16 minus 1 factorial, that is 15 factorial ways. The event that the two particular professors are on either side of the Vice Chancellor. Now two particular professors can occupy the seat on either side of the Vice Chancellor. That is in 2p2 ways. One is the left and right. Therefore, the 2p2 ways. After remaining 13 professors and one group of the two particular professor and the Vice Chancellor, altogether, that is a 14 can be. That is a total is a 14 can be seated on a round table in 14 minus 1. Whenever there is a round table, then we treat it as a 14 minus 1 factorial. That is equals to 13 ways. 13 factorial ways. Therefore, n of a is equals to 2 into 13 factorial. Therefore, P of a is equals to n of a upon n of s. That is a 2 into 13 factorial upon 15 factorial. And this is the 1 upon 105. This is the P of a. Now the next is 15 professors have been invited for a roundtable conference by the Vice Chancellor of a university. What is the probability that the two particular professors occupy the seats on the either side of the Vice Chancellor during the conference? The 15 professors plus one Vice Chancellor, and the total persons are the 16. 16% can be arranged in a round table that we have learned in the permutations. 16 minus 1 factorial, that is equals to 15 factorial ways. N of s is equals to 15 factorial. The event that the two particular professors are on the either side of the Vice Chancellor, the two particular professors can occupy the seat on the either side of the Vice Chancellor in 2p2 ways, that is the 2 ways. After remaining 13 professors, that is, and one group of the two particular professor and the Vice Chancellor, that is altogether is a 14 can be arranged on a round table in, that is equals to 14 minus 1 factorial, that is a 13 ways. Therefore, n of a is equals to 2 into 13 factorial. P of a is equals to n of a upon n of s, 2 into 13 factorial upon 15. And that's why that is a 2 into 13 factorial into 15 upon 15 into 14 into 13 factorial. Therefore, P of a is equals to 1 upon 105. The problem number 17. A bag contains 7 black, 4 red balls. If 3 balls, are drawn at random, find the probability that 1. All are black, One is a black and two are red. 3 balls can be drawn from 11 balls in 11C3. Therefore, 11 factorial upon 11 minus 3 factorial into 3 factorial. And it is written as 11 into 15 n of s. Now 1 first. A, the event that all balls are black. There are the 7 black balls and 3 balls can be drawn from these 7 black balls in 7C3 ways. N of A is equals to 7C3 and that is equals to 7 factorial upon 7 minus 3 factorial into 3 factorial. N of A is equals to 35. P of A is equals to N of A upon N of S. That is 35 upon 11 into 15. That is 7 upon 11 into 30. Therefore, P of A is equals to 7 upon 33. Second, let B is equals to the event that 1 is a black and the 2 are the red. Therefore, 7C1 into 4C2 so we have N of B is equals to 7 into 6. Therefore, P of B is equals to N of B upon N of S, 7 into 6 upon 11 into 15. Therefore, P of B is equals to 14 upon. Again, I am repeating here. A bag contains the 7 black, 4 red balls. If the 3 balls are drawn at random, find the probability that are they black, 1 is a black and the 2 are the red. 3 balls can be drawn from the 11 in 11C3 ways. That is equals to N of S is equals to 11 into 15. Let A be the event that the all are the black. There are the 7 blacks. Therefore, the 7C3. N of A is equals to 7C3. N of A is equals to 35. P of A is equals to N of A upon N of S. That is a 35 upon 11 into 15. 7 upon 11 into 3. Therefore, P of A is equals to 7 upon 33. B be the event that 1 is a black. Therefore, 7C1 into 4C2. Therefore, N of B is equals to 7 into 6. Therefore, P of B is equals to 14 upon 55. And in this way, we have completed this exercise, which is the 9th. We'll see in the next video. Till then, goodbye.